Okay, so good afternoon. We start today's session. Today we are going to study session 4. Session 4 is about the network of the sensor. So you remember in session 1 we have studied the basic knowledge about robotics, and in particular we have studied the definition of the robot, the history of the robot, application of the robot, right? And we have also studied the way how to design or the basic guideline for the design of the robot. And in particular, you understand inside any robot, we must have a mechanical system, control system, and software system, right? And inside the software system, we have studied one lecture about the equation of motion, right? So you will see robotics is a course which has connection to another important course, which is machine intelligence or AI or artificial intelligence, right? And the module which we have made as a connection from robotics to AI or to machine intelligence is the module which is about motion planning, right? So we take the task as an input, we must decompose the task all the way into the equation of the motion. We have studied the basic knowledge behind the equation of a trajectory, right? So you remember, we need to come out with time function for all the coordinate to be performed, right? So that's about the basic knowledge that you have studied within 3 hours, right? So in session 2, we have studied automation. And in particular, we have studied industry automation. So you understand, inside manufacturing system, we have a production system. Inside the production system, we have automation system. Then inside automation system, we have control system, right? And the key takeaway from section 2 is for you to know that there are 4 design methods, okay, for you to use in order to design the control system. But the good news for you is you can apply these 4 design methods to design control system inside a robot. So therefore, topic section 2 and section 1 are strongly related, right? On top of automation system, we have studied little bit of the mathematics for you to know in order to manage the production line, right? So that is quite interesting knowledge for you to know. Okay. Then in section 3, we move on to study the basic skill or technique for you to use in order to build up a network system. Okay, because the third topic for this course is about the IoT, right? And then you understand section 3 actually help you also to understand robotics, because a robot could be considered as a mega actuator and a mega sensor, right? So all the knowledge which has been spread over these 3 major topics, robotics, the automation, and the IoT, could be put together, right? So then in section 3, we have studied the principle at the lowest level in any network, right? So at the lowest level, you only have 2 technique or 2 principles for you to construct a network. One is called as synchronous serial communication technique, right? Second one is synchronous serial communication technique, right? So with the use of these 2 principles, you should be able to design your own version of protocol for higher level communication, right? So it should not be dominated by what you have heard about HTTP or whatever, right? Actually, with the use of synchronous serial communication and asynchronous serial communication, you can define or invent your own version of higher level protocol for data communication, right? So in section 3, we have studied this two fundamental principles for you to know how to build up a network. And during the study in section 3, we have learned a little bit skill about how to make use of ARM Cortex MCV microcontroller. Because ARM Cortex MCV microcontroller are very powerful, right? For example, with synchronous serial communication, you can easily use the ARM Cortex MCV microcontroller to build a two-dimensional network Java, because each node support full communication with the use of synchronous serial communication, right? But if you switch to asynchronous serial communication, then you can easily build up a three-dimensional network, because for each node of ARM Cortex M4, for example, you have you have the support of a port for the synchronous serial communication. Then in this way, you can construct three-dimensional IoT, right? So this are the quick summary of what you have learned so far, right? And you can also consider a robot is a mini version of IoT, and inside the robot itself, you need to connect different modules together, right? So the knowledge and the skill learned in section 3 are also applicable to the design. So in future, if some of you are very interested in doing the design of the robot, you can apply this knowledge and skill. Okay. Then for the remaining two sections, section 4 and 5. Section 4 is for you to know how to attach sensor inside the network, right? And today we are going to learn two types of sensor. One is called as an analog sensor. Second one is called as digital sensor. So you need to know, okay, basically, if you classify the sensor according to the type of data which will be output from the sensor, you only have two types, analog sensor and the digital sensor, right? And in today's study, we will know how to interface, right, sensor with network. Then again, we will use ARM Cortex as an example, right? So with the knowledge learned from this section, I guess you can easily understand how to integrate sensor inside a robot, how to integrate sensor inside a production line, right? Then tomorrow we will study the way how to interface or attach actuator into a network, right? Okay, so today we are going to have three lecture, right? The lecture is for you to know what is a sensor, and I will going to show you one or two examples about analog sensor and one or two examples about digital sensor, right? Then subsequently, we need to know how to interface with the analog sensor and how to interface with the digital sensor, right? Okay, and today's study is equally applicable to the topics of robotics and automation. Okay, so let's look at the sensor, typical sensor that you may encounter when you construct IoT in general, right? I believe in section 3, you know that the popular sensor inside IoT should be temperature sensor and humidity sensor, right? Because once we construct an IoT, we need to monitor, okay, the temperature distribution, humidity distribution in the city, for example, right? So these are the two very important sensor for you to know what should be the working principle, etc. Right? And for digital sensors, the typical example should be the encoder or digital sensor inside motor. But you understand, inside a robot, we have a motor. Inside a production line, we have a motor. In order to control the position and the velocity of the motor, we also need to have a sensor. And the popular sensor inside the motor should be optical encoder, but this is another name, okay? But optical encoder basically means digital velocity sensor or digital position sensor, right? Okay, this is just for you to know. So let's start with temperature sensor. In our university, we have dedicated the course of our students to study all kinds of sensors. So our student will spend at least one semester to learn all kinds of sensors. Okay, but for you, we just spend one lecture to cover the two typical example of sensor, one in analog domain and one in digital domain. Okay, so this video will give you a lot of idea about what is a temperature sensor. I've got no voice.
Protocol negative temperature coefficient with NTC thermistors. I couldn't find a thermistor locally, but some quick research turned up that automobile cooling temperature sensors adjust thermistors in a productive case, which was a good thing since I'm saving me having to make a case of my own. With this one, there's only one obvious place to connect to, this threaded wire. So where do the two thermistor wires go inside? Well, one goes to the threaded wire, and the other goes to the brass case. So I wrapped one wire tightly around the case, and after attaching the ring terminal to a wire and finding suitable nuts, I attached another wire to the threaded wire. I then connected up a meter and put it on a resistance scale. Remember, the resistance changes with the temperature. Put my fingers on the probe part, and it started to heat up. Sure enough, the resistance on the meter started to decrease as the temperature increased. So it contains an NTC, or a negative temperature coefficient. To be useful, I needed to know what resistance matches what temperature. Unfortunately, I couldn't find a resistance temperature table for this particular one. So I had to make my own. To do that, I prepared a tall container with a soda can with all the paint sanded off. I filled it with water and put the probe part of the sensor in the water. I also put in my kitchen thermometer. The long length of my thermometer is why I went with a tall container. For my purposes, I needed to know the resistance to temperature values for temperature to be able to freeze the point of water. So I put the whole thing in my freezer until the thermometer read near 0 Celsius, or 32 Fahrenheit. Then I took it out, connected my meter to measure resistance, and put it on my stove heating element. I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius, or 212 Fahrenheit. And here's the chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I've gone through this process was to do some experiments to determine if cold water boils faster than hot water, as some people think it does, and to find out why it might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I covered in another video I'll point out later. Here's the fun I had making the PC fan turn on and the thermostat gets too hot. First, here's the circuit without the thermostat. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with the thermistor. The positive from the power supply goes to one end of the thermistor, The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. The fifth time when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, even so it has a high resistance. The fan needs a certain amount of electrical current running through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan. And the resistance of the thermistor is high enough to make that current too low. That means this hair dryer to heat up the thermistor. That causes the thermistor resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Wow,
Okay, so this short video basically help you to understand the sensing principle. So the sensing principle is to find the sensing element which will convert the physical quantity of the measurement into machine readable value. All right. So the typical sensing element come from electric domain. For example, we can use resistor to serve as a sensing element. We can also use capacitor to serve as a sensing element, or use an inductor to serve as a sensing element, right? So, for example, in this video, you see we use a resistor to serve as a sensing element to pick up the value of a temperature. And then inside the video, you see there are two types of resistor. One, we call it as an NTC. NTC, negative temperature coefficient. It means what? When temperatures go up, resistance value goes down. Right? You can also have a PTC, positive temperature coefficient. When temperature go up, resistance also go up, right? But typical example is NTC, right? So basically it means we can convert or relate temperature to resistance. Once you have a resistance, it's easier for you to convert resistance into voltage, right? And once you have a voltage, then the good news for you is we have this analog to digital converter. Then you can easily convert voltage into a digital number, right? Okay, so that's for you to know. And in order to come out the different type of sensor, the measurement of temperature, it is very important for you to know some physics which relate temperature to other physical quantity. All right. For example, I don't know, maybe you may have already forgotten about what you have learned in year 1 physics. Okay. If let's say we have an ideal gas, so you understand all the material could be exist in one of these three popular states: solid, liquid, and gas. All right. So if the object are in the state of the gas, then we have this ideal equation of or equation of ideal gas. So you see, PV means pressure times volume is proportional to temperature T, and R is a constant, and represent the amount of gas is a molar number, etc. Right? So immediately you see pressure related to temperature, volume related to temperature, right? Another thing is about how to increase temperature of the object or mass. How to reduce the temperature of the mass. So this equation is very important, right? So you will see Q is amount of energy inject or remove from the mass, right? Then theta T is increase or reduce of the temperature. N means it's a mass, C is a coefficient, right? So these are the basic equation for you to know, right? And also you need to know the transfer of the heat, because the temperature is a something which is related to thermal energy. And in electric domain, temperature is very much similar to voltage. So you understand when you apply the voltage to certain electrical device or electronic device, then you will see the current flow through. But once there is a temperature difference, you will see a flow of the heat or flow of thermal energy, right? So think this equation similar to the equation in electric domain. There's a T1 minus T2 like voltage difference. Then you will see the current flow. But here is a small q. Q is a flow rate of heat. Heat means thermal energy, right? Okay, so just for you to know. And convection means transfer of the heat between solid and material in another state. For example, air or gas. Okay, you have a media or object in the form of gas. Another mass in the form of solid. Then between these two material or substance, there is a heat transfer, right? This, the English name is a convection. If let's say inside the solid, because one end has a higher temperature, another end has a lower temperature. The inside, we call, if you have this kind of heat transfer, we call it as a convection, right? We can also see the transfer of heat through the radiation. It's a electromagnetic wave. Then in this case, the amount of heat transfer is proportional to the temperature raised to the power of 4 or something like that. Okay. And another phenomenon is quite important for you to know is about the relationship between the geometry of material and the variation of temperature. So you can see when temperature increase or reduce, the length of the material will reduce or increase, right? But this is correspond to the scenario we only allow the material to vary in one direction, right? And in general, if we do not restrict the direction of the variation of the material, and that is the general situation. When there's a temperature change, there is a volume of the materials change, right? So this has a volume expansion. Okay. So based on this understanding about the relationship, okay, between temperature and other related in the physical quantity, then we can come out different type of solution for the design of a temperature sensor. And this slide highlight to you 4 popular ways of designing sensor for the measurement of temperature, right? So, for example, okay, volume expansion method. I guess this product is familiar to all of you in the medical field. You can buy this thermometer very cheap from the shop, right? Then you can easily monitor the body temperature. Okay, and the inside you will see we have a liquid. So when the temperature changes with volume expansion, then the liquid will travel, move inside the tube. Then once we calibrate this instrument of the measurement, then we can get the accurate reading about the temperature, right? So this is the example which indicates the reading of the 40 degree, 25 degree, 15 degree, 0 degree, etc. Right? So this is a very, very simple way for us to do the design of temperature sensor. This is another design principle which make use of the different expansion coefficient demonstrated by different type of metal. So you just use the 2 different type of metal, put them together due to the difference between the volume expansion coefficient, right? So when the temperature increase, these 2 metals will expand differently, then you will see the diffraction in certain way, right? So then based on this property, we can first convert this diffraction into resistance, okay, or other physical quantity, okay. So this is another working principle. And here, for this slide, we showing you that you can put the 2 pieces of metal, okay, face to face. Then you will see the diffraction in one direction, right? But you can form this heat, okay, units, right? So it's like a two coin, okay? So we have two coin made of two different type of metal, right? Then you superimpose them together. And then in this case, due to the difference in the expansion coefficient, then you will see the needle will undergo angular rotation. Okay, then use this type of motion to provide the reading about the temperature, etc. Okay, this one is also a very interesting working principle for us to follow in order to guide the design of temperature sensor. So basically, it means we also have two pieces of metal. Okay, metal A, metal B, they have different property. Then in this case, we form two junction of the T1, junction of the T2. Then you will see when T1 is not equal to T2, then is a voltage built up inside this loop, right? So for example, we can hold one junction at a constant temperature, another end as a measurement terminal to measure any unknown temperature, right? So therefore, the voltage observed inside the loop is proportional to the difference between these two temperature. Okay, and this is one design example. So you will see you have a T1, T2. T1 is being held at a constant temperature, right? T2 is a temperature under measurement. T2 could be any value of the temperature measurement. Okay, here you will see we have a cold junction compensator. So basically, ideally we want the T1 to be 0 degree. If T1 is not equal to 0 degree, that means the T1 itself will produce a voltage. Then we use this junction compensator to supply negative voltage, right? To make the reading to be 0. So actually, you do not need to hold T1 to be 0 degree. As long as the T1 is a constant, okay, he will have nominal voltage. Then we just supply negative voltage in VC, and the VC cancel the V1. Then it's equivalent. You obtain the situation in which T1 corresponds to 0 degree. Then whatever you measure the T2, then T2 has a reference at the 0 degree, right? The reading from T2 is reference to 0 degree. Okay, so this is just for you to know. So in the video, the very popular one should be resistor. Okay, so we have special type of resistor. Resistance is a function of temperature, but we give this one this device the name we call thermistor, right? The thermal resistor, right? And in the video you see popular type is this NTC thermistor, right? So when temperature increase, the resistance value will decrease, right? So and in the market you can buy a lot of resistor. Okay, then how to convert resistance into voltage? So it's very simple. You just put a circuit with two resistors. One resistor is a thermistor, right? So the resistance value change as a function of temperature. Another resistor is a resistor with constant resistance, right? So based on this circuit, you will see output voltage is a function of R1. R1 change with respect to the temperature, right? So I guess this is a very simple circuit for us to know in order to convert resistance into voltage. Okay, but once we have a voltage, then we can convert it into digital number with the use of microcontroller, right? So always remember, microcontroller has a built-in module which allow us to interface with any analog voltage. As long as we are able to convert, okay, any physical quantity into a voltage, then we should be able to convert it into a physical number, right? But here you may ask this question. You see relationship between temperature and resistance is not a linear relationship, right? But this these kinds of non-EMP could be easily rectified by calibration, right? So you do a calibration, you have an equation to rectify this non-EMP. Okay, so mathematically this is not an issue, right? So you just know. So once you are able to convert temperature into digital number, always remember you need to do calibration. That is a process we call it as calibration, right? So calibration is just to find the equation, right, which will transform digital number into a linear relationship between the exact input of the temperature and the reading of digital number, right? So, for example, this is not linear, okay, because the relationship between temperature resistance is not a linear relationship, right? So it's quite easier to find the curve to fit this one. Once you know the curve fitting, then immediately you know how to rectify the reading. Okay, so it's not a big issue. Okay, so it's a quite simple one. And once we are able to relate temperature into resistance, then how to interface it with the microcontroller? Actually, this gives you an example of interface semester with a microcontroller, but this one is not an example of ARM Cortex, it's Arduino, right? But you look at the outside of this microcontroller, it's very simple. You have two resistors, one with a constant resistance, another with a variable resistance, right? But the power supply comes from a microcontroller, and the microcontroller provides the power. Okay, so this helps you to know how to interface with microcontroller. Okay. Then, okay, second example of analog sensor should be the humidity sensor, right? So why I use this humidity sensor to illustrate the nature of analog sensor. The reason is because humidity is a physical quantity which is strongly coupled with temperature, right? So these two physical quantities are strongly related to each other, right? And humidity control is quite important in agriculture. Humidity control is also very important inside a building with a lot of residents, because in Singapore, I guess all of you know, okay? So here is quite humid. So that means for the comfort of our own living, we need to control humidity. And then in agriculture, this video will highlight to you that the humidity control is also extremely important, right? So you remember IoT could be deployed in industry, right? In the production line. And even inside the production line, you have a lot of human worker. Then you need to control temperature, control humidity. Otherwise, the worker may not feel comfortable, right? And the IoT could also deploy in agriculture, China, and for the farmer and eventually vertical farming, etc. We need to control temperature, control humidity altogether. Okay, so this video just explain to you the necessity for us to control humidity in agriculture.
And today we're going to talk a little bit about humidity and controlling humidity in your greenhouse or in your warehouse growing operation. So the effects of poor humidity management is a lot of time when you end up with humidity ranges outside of the ideal. So different crops prefer different humidities, and they function differently in different humidities. Additionally, if you have different humidities, sometimes it impacts the final product, not just the growth of the plant. So it's really, really important to understand humidity, what your humidity is, and be able to manage your humidity within a certain range in the growing environment. So for most growing environments, optimal humidity levels for most crops will range between like 85% humidity and 60% humidity, somewhere in that range. Most crops fall in 75 to 85% humidity range, ideally, but a lot of crops are very comfortable exceeding that. A lot of crops are okay going under that. So when things get too humid, and too humid again is a very subjective term, but if things are too humid and you're starting to see disease or fungal pathogens show up on your plants and you're struggling with some of these issues, you probably got a bit of a humidity problem and you need to know how to dehumidify. There are a lot of ways to do this. If you live in a dry environment, then oftentimes air exchanges will take care of the problem for you. Or you can rely on air conditioning, which dehumidifies through kind of the by condensation. Or you can use an industrial dehumidifier or even a home and hobby dehumidifier for a smaller operation. So a lot of folks ask about cooling walls. Well, cooling walls, swamp coolers, that kind of thing, they work in really dry environments because they're dumping water vapor into the air, right? So that's why they work, which means that they're actually adding humidity to the air. That's typically why they're not super effective at very high humidity levels and why they work so well in dry environments. Those types of cooling things, typically, if you're growing in a greenhouse that uses the cool wall effectively, you probably don't have a humidity problem because you're already in a place with really low humidity. So humidifiers and sizing them can be a really tricky subject, especially when it comes to plants. In traditional engineering, they know how many people will be in a building exhaling, they know what the humidity level of your breath is, they know what the humidity levels outside are from season to season, they know all of the different things that are contributing to humidity in that environment. But indoor growing is such an early industry that it's really pretty up in the air as to how much water plants are oftentimes dumping into the atmosphere. So this can be a pretty tricky subject, but if you're already growing indoors, you know how much water your plants are consuming, right? Because you're having to top off your sump tank. The difference that you're topping off your sump tank, a significant amount of that is just transpirational losses from your plant. So they're just dumping that water into the growing environment. That's usually a good place to start. We also have some humidity calculators and some water vapor calculators on Able for doing CO2-based vapor, basically pounds of water type calculations. That could really help with narrowing down what size of humidifier you need. By and large, with our zip farms, with what we do, we tend to recognize, we tend to use one fairly large industrial indoor humidifier for about every 500 square feet. And that's usually more than enough to take care of our humidity problems. So,
okay, this should be good enough for you to roughly know, right? So necessity for us to control humidity in agriculture. Just now I mentioned in our living space,
Indoor
it's
residential
also important.
reducing humidity of the source, improving indoor ventilation, dehumidifying, and improving thermal window energy efficiency to prevent condensation. Condensation forms on cold surfaces as surface temperatures fall below dew point. Humidity increases with the amount of people and activities in the home. Showers, laundry, clean dishes, and unfinished crawl space areas can cause indoor humidity to be unnecessarily high. In conventional Canadian homes, it becomes necessary to reduce indoor humidity with the onset of winter. As a rule, 30 to 35% indoor humidity is recommended for -5 to -10 degrees Celsius. When tackling indoor humidity, always improve the areas where the moisture is being generated. Installing good quality bathroom fans and cleaning the unit seasonally will help keep the exhaust fans effective. Cooking range and other exhaust fans should be directly vented to the exterior and not into the roof perimeter soffit. If you have a forced air furnace, check to see if you have a fresh air intake. Fresh air intakes make all the difference in reducing indoor humidity in the winter, that is, providing that they are working properly. These units often require seasonal cleaning and should be located where good quality air can be drawn into the home. Fresh air intakes should be located well away from vehicle exhaust, pellet stove exhaust, and close dryer exhaust vents. You can monitor your indoor humidity levels with an inexpensive humidity gauge or use a wall-mounted dehumidistat switch connected to an exhaust fan. Dehumidistats are most effective when connected to a forced air furnace fan, which has an outdoor fresh air intake as part of the return system. There are two main types of dehumidifiers for residential applications. Each type must be correctly sized for the task. Dehumidification may not be necessary if the indoor humidity source can be controlled. Whole house dehumidifiers are more common in coastal climates due to outdoor humidity levels. High humidity in some rooms can be problematic. Kitchen, bathroom, and bedroom windows can collect moisture or frost as the glass cools below dew point. Consider upgrading to thermally efficient windows in these rooms or cover the glass with plastic to prevent condensation from forming. This prevents the moist indoor air from contacting the cold glass. Ensure that the plastic is well sealed for the plastic barrier to work properly. Protecting basement windows and skylights from the elements reduces condensation and ice from forming inside the building. These are my insulated skylight covers that I constructed and I put in place each fall, which are highly effective in saving energy, reducing moisture, and preventing roof ice.
Okay, this should be good enough, okay? And then how to find the sensor element which allow us to convert the physical quantity of the humidity into computer readable value, and then eventually convert into voltage into digital number, right? So from this example, you will see, just like I mentioned, humidity and the temperature are two physical quantity which are strongly interrelated to each other, right? So
From howmechatronics.com. In this Arduino tutorial, we will learn how to use the DHT11 and DHT22 sensors for measuring temperature and humidity in the Arduino board. These sensors are very popular for electronic hobbies because they are very cheap but still providing great performance. Here are the main specifications and differences between these two sensors. The DHT22 is the more expensive version, which obviously has better specifications. Its temperature measured range is from -40 to +125 degrees Celsius with 0.5 degrees accuracy, while the DHT11 temperature range is from 0 to 50 degrees Celsius with 2 degrees accuracy. Also, the
okay, so I'm not going to play the full video, but just pay attention to the sampling rate. You see the third row. Sampling rate is 1 Hz, another one is 0.5 Hz. So remember this number, so it means what? In order to maximize humidity, you need to take time, right? So it's not like the temperature or other physical quantity, you can do the maximum is a very short period of time. 1 Hz means what? 1 second reading, very slow. So this just for you to know. Okay, so the rest should be okay. So basically in the video you mentioned you can purchase right sensor which has built-in temperature sensor, humidity sensor, and the read the data, etc. Right? Okay. But in future, if let's say you want to design your own sensor for the measurement of humidity, then you need to know what is the phenomenon of humidity, what are the equations that we will use, okay, in order to guide the design of a humidity sensor. Okay, so physically basically means what? Humidity means there is the presence of water vapor in the air. Okay, so basically we know that every substance or matter could be exist in solid state, liquid state, and gas state. Okay, gas, water gas has another name. It's called as water vapor, right? So once you have a lot of water vapor in air, then you see the humidity level is very, very high. Okay, so this slide help you to understand the transition for matter from liquid state to gas, gas back to solid, solid to liquid, etc. Right? So in the video, you will see this terminology of condensation. Condensation basically help you to understand about the presence of water in air. If inside the air there is no water, there is no condensation. Right? So this is the evidence for you to understand. So inside the air, we have a lot of water vapor, right? And because of the water vapor, then we feel the environment is humid, etc. Right? Okay, how to, I guess this is also a basic physical phenomenon, right? So inside the air, if you place a surface at a certain temperature, but there is another critical value of the temperature, we call the dew point. So in the winter, you understand, even in summer, like you take out the soft drink from the refrigerator, you place on the table, you will see on the surface of the soft drink a lot of water appear. That is a phenomenon of condensation. Condensation means if the temperature of the surface is below the dew point, then the water in air will become will make a transition from gas into liquid state, right? And you look at the curve of the line, basically you see the dew point or the critical temperature value is a function of the temperature of the air, right? So you remember there are two temperatures, the temperature of the surface, temperature of the air, right? So it depends on the temperature of the air. Then the dew point on the cool or cold surface is different, right? So this is the this way of really interpret, okay? And based on the dew point condensation process, you can easily explain how come in the sky we see the cloud. The cloud actually is not the water vapor, is water liquid or tiny particle of water in the state of liquid. Okay, so this help you to understand why you see the cloud in the air, right? Okay, so and we can make use of condensation to purify water because it's a very interesting physical phenomenon. Okay, so this is an example to illustrate. Okay, your input water will be very dirty, right? Then you convert water into water vapor. The water vapor pass through the surface. The temperature of the surface is below the dew point. Then the water vapor will become back to water liquid, and then in this case, the water liquid is a pure water, drinkable water, right? So this is something for you to know. And you can also use the water vapor condensation to recycle, okay, the cooling water, because once you cool a turbine, then water become vapor. Then how to make the water vapor back to liquid? They use the liquid to cool the power generator, right? So this help you to understand, okay, how to make use of condensation to recycle water vapor, right? And deposition is a phenomenon for the substance to make the transition from gas directly to solid without going through liquid. Normally, gas become liquid become solid, right? But for those of you, you know, northern part of China, and you see this kind of phenomenon, right? So this is also an evidence about the presence of a water vapor in air, right? Otherwise, you may not see the glass on the surface of tree, etc. Okay. Evaporation, this is a phenomenon in Singapore. You see how come we are so we are in a place so humid, and the reason is because of high temperature, and we are surrounded by sea water. Then water will make a transition from liquid state into gas state, okay, etc. And for animal, in the same, if the body of the animal's temperature is higher than the ambient temperature, then you will see the radiation, etc. Okay, and if the ambient temperature is higher than the body temperature, then you will see evaporation, etc. Right, the humidity in the air will increase, etc. Right, so this is for you to know. And again, this slide helps you to understand the humidity is a function of temperature. You see, temperature go 10 degree, 20 degree, 40 degree, and relative humidity, the relationship between humidity and the presence of water vapor is different, right? So it means that the humidity and the temperature is strongly coupled together, right? Now, okay, since we know the nature of humidity is related to the presence of water vapor in air, then this understanding help us actually to come out with a solution to convert the percentage of water vapor which present in air into something which are related to electric quantity such as capacitance or resistance, right? For example, if you have a material, right, which serve as a resistor, when there is a presence of water, that means the conductivity will increase or resistance will reduce, right? So this is a guiding principle for us to come up with a solution which allows us to convert humidity into computer readable number, right? Okay, so and you can also use a capacitor. So you remember capacitor is consists of two parallel plates, but in between we can insert special material. We call it a dielectric material. This material is not electrically conductive, right? The current cannot pass through. But however, if you increase the humidity, this is absorb the water, right? Then it will increase the capacitance of capacitor, right? So it's like this illustration. Between these two parallel plates, you have a dielectric material, right? When this material absorbs the water, capacitance will increase. Okay, so this is the way to pick up the value of humidity, convert it into capacitance. Once we have capacitance, it is easier for us to convert capacitance into voltage, right? Okay, so then this curve is showing you relationship between humidity and capacitance. Then convert capacitance into voltage. Then you see is the relationship is proportional, right? That means the output voltage is proportional to the level of humidity, right? Okay, so and then we want to know exact definition of humidity. Okay, mathematically you can say within a certain volume of air, then we just compute the amount of water vapor. So this is a mathematical definition, right? Pure theoretical definition. The amount of water vapor which is present inside a fixed volume. If you compute in this way, basically means what? The amount of water per unit volume. That is absolute humidity. A unit volume, what is the amount of water vapor? But this number is not inclusive, right? If let's say you go inside a room, then we may feel this is humid, not humid. But our brain cannot relate such a feeling to this number. So this is not deep, right? So does not help us to interpret. So this is why later on we will see another definition, which is about the relative humidity. Relative humidity is inside a room, you will have 100% level of humidity. Then our body, our brain can remember, this looks like 100% humid environment. But if you enter another room, which is less than 100% humidity, then our brain can remember the feeling, right? So relative humidity is more intuitive, right? And then our mind could interpret it. But this one difficult for our brain to interpret this number. Okay. But mathematically we can compute. So you remember we have the ideal gas equation. We can use this equation to come out and approximate the solution, right? So you see PV related to T, right? N means it's a molar number, right? And the molar number is equal to the mass of water divided to the molar mass of water. Capital M of water is constant, right? So based on this formula, immediately we can compute the presence of water vapor per unit volume. You see, M a small mass, okay, vapor divided by volume, right? Then you can get obtain this equation for us to compute, okay, the mass of water per unit volume. Okay, that gives us an idea about the absolute humidity, but this one is not intuitive. We cannot, our mind cannot interpret it. Okay, but this is a pure mathematical solution. Okay, And this one is unique to human being, right? We can always have a room, a reference room, 100% unique. That serves as a reference, right? And our body can remember, once you enter such a room, well, you have a feeling, right? But once you enter another room less unique, then our feeling is different, then our mind can remember, okay? So this is why we use this definition, relative humidity. That means that is the ratio. Okay, let's say in one room you have a maximum humidity, and the inside you have either maximum pressure or maximum we call it a molar number of water, right? So then you go to another room which is less humid. Let me just compute the ratio, right? So the pressure over maximum pressure or molar number of water over the maximum molar number, right? So this is a relative humidity. Okay, so then this is the equation, and then this is the illustration to you. Let's say inside a space you have 95% of a relative humidity. Okay, so you have a pressure, but volume is the same. You see V is the same, temperature is the same. Only P1, N1 is different. P2, N2 is different. So for the second scenario, same volume, humidity just 10%, right? Then you compute the ratio, then you can have a feeling. So our body can remember. And this is just background knowledge for you to know, right? So with the same amount of presence of water vapor per volume, if we increase the temperature, okay, we do not increase the amount of water vapor. When temperature increase, then relative humidity, we will feel less humid, right? Humidity we feel in your job, right? So this is and this is explained by this equation, right? Volume is the same room, we don't change the room, right? When we heat up, the temperatures go up, the pressure can also go up. Then you will feel less humid. This is like in the southern part of China. If let's say you go to a room in the winter, if the room temperature is very low, actually we will feel it's very humid. But once you warm up the room temperature, you will feel comfortable, right? So this is explained by this equation. Okay, it's just for you to know. Now come to this question. Okay, in future, if let's say you want to design by yourself, okay, the sensor which allow you to measure humidity. Okay, then what are the popular principles you to follow? So here you see there are 3 popular physical principles for you to apply in order to guide the design of humidity sensor. Or at least these 3 principles allow you to understand the design of a humidity sensor done by others. Okay. First one is to, just like I mentioned, is to convert humidity into resistance. So you will see, because water has a conductivity in electricity. More water you have, then the current could easily pass through. So it means what? Resistance will reduce, right? So then you can have a piece of material which serves as a resistor, right? Expose it to the air. Then if you absorb water, then resistance will reduce. Then the variation of resistance actually is a function of humidity, right? So it's quite easier for you to understand. Okay, so you can see this is the relationship, right? So when humidity increase, resistance will reduce, right? But this is not linear relationship. Okay, here I'm showing you the calibration equation. You just do the curve of 15, right? So once you have a resistance, then you can calibrate what should be the exact value of relative humidity. So you see, this is a we call calibration equation. You do the curve 15, right? And then this can be remembered by your microcontroller, right? So once you have a reading about the actual resistance, then you use this equation to compute the exact value of relative humidity. Understand? So this we call calibration, right? Okay. So, and this is a real example. Then you see all these printed circuit like that. Actually, it is a material which serve as a resistor, okay? So quite straightforward. Then once you have a such humidity sensor, then you can integrate them into device. This device could be mounted on the wall inside a building, etc. Right, etc. Okay. Second principle is to convert. Just now I mentioned convert humidity into capacitance. Right. So you remember, capacitor is very simple. Two parallel plate. Always remember between the two parallel plate, you could have air. That means it's empty. Okay. But this kind of capacitor does not allow you to pick up the humidity. You can insert a special material we call dielectric material, right? So that dielectric material will absorb water vapor in the air. When more water absorbed by this material, then capacitance of the capacitor will increase, right? This is the way to relate our capacitance to the variation of humidity, right? So, and in the video that just now I'm showing you, actually inside, you make use of this working principle to design humidity sensor, okay? And then you will see relationship between relative humidity and capacitance, right? So then you can use, when you look at this relationship, more or less like a linear relationship, except there is offset E, because the straight line does not pass through the origin. This is why you need the B to bring up or bring down, go to the origin, right? Origin means when relative humidity is 0, I want the reading to be 0. And how to get the reading to be 0 is the B. B will shift it down, right? So again, this A times C plus C is a calibration equation, right? And because this is a linear relationship, then you just use polynomial equation of V1, right? Okay, but B is play the role to bring down to and force the straight line pass through the origin. Okay, so this help you to understand the concept of doing calibration, right? Okay. And in the video just I mentioned, ask you to look at the response time, 1 plus 0.1 plus, etc. And again, you look at this rise time. These are the commercial sensor. Normally you see quite slow, 15 seconds, and some you may have 2 to 5 minutes. Okay, then 5 seconds, 3 to 5 seconds. Okay, so this help you to know. Okay, you cannot do fast reading or measurement of humidity. Okay, so this is basic knowledge for you to know. Okay, so I just cover these two analog sensor. The working principle, the philosophy is very important. Philosophy is very simple, right? Regardless what is the physical quantity, which could be pressure, force, right? Many other things like lighting, for example, right? Intensity or acoustic signal, whatever, right? So principle is to convert the value of any physical quantity of the measurement into a physical quantity in electric domain, such as resistance, capacitance, inductance. Once you have a resistance, capacitance, inductance, then you can easily convert them into voltage, right? Once you have a voltage, then you can convert voltage into digital number. So this is the working principle for any analog sensor. Understand? So in the previous slide, you have studied 2 examples. Then for all the rest analog sensor, they follow the same procedure. Understand? Okay. Here. Now we jump to digital sensor. This one is also quite popular. Try to understand the physical principle behind the design of digital sensor, right? So digital sensor means what? We want the output to be digital number, like the 0101, or sequence of the 0101, or regular pulse waveform, 01010101. Then we count the number of the pulse, right? So this is a working principle, okay? So you can apply this working principle to do the measurement of many other physical quantity. Okay? But here I use two popular example in robotics because and even in automation production line, right? In robotics, you see robot can perform motion job, right? So position, velocity are two very important physical quantity which are related in motion. When we talk about the motion, we might talk about position, we might talk about velocity, right? And once you know position, velocity, you can easily compute acceleration. Okay, so these are the two popular examples of digital sensor. Try to understand the philosophy behind the design. And here, okay, this slide illustrates the rotary motion because you see even for our body, we can undergo angular motion. This is our arm, finger, all are angular motion. So you see, so angular motion should be the popular motion inside a human life and robot, right? Because for our body, actually we can only undergo angular motion. But through the combination of angular motion, we can output linear motion. But this linear motion is based on the control of all the independent angular motion. Okay, but in terms of independent control, all are angular motion. Okay, so for angular motion means you have a rotation about a single axis, right? If you have 2 degree freedom, then you have 2 axes. Through the combination, then you can produce a linear motion. Okay, so as long as we are able to compute or measure or convert location about the single axis into digital pulse or square pulse waveform, good enough already because the microcontroller can count all these transition from low to high, high to low. Okay, now you need to know what we mean by the pulse or square waveform, right? And you just pay attention to the transition of 0 to 1, 1 to 0, 0 to 1. All right, you see it 0, 0, 1, 1, 1, 1, 0. All this is a pulse, right? Transition. Good enough already. Then how to convert it? You see, when there's a location, we have a window. You see the dark area and the white area. So the light can pass through. I guess you see you have a LED channel. LED means it's a light source. So you can pass through the white, the whole window. Once you pass through, another side you see the terminology photo sensor. You see photo sensor LED. Once the photo sensor receives the light, then there's a transition either from 0 to 1, 1 to 0. Okay, so this is the way to produce the series of the transition from 0 to 1, 1 to 0. Right? Okay, so this is the working principle. Now this is summarized. You see, look at the smaller disk with one ring of a hole. You see, at the outer edge, you have a one ring of a hole, right? Hole means what? When the hole align pass through between light emitter, you see, you have a light transmitter. Transmitter means a light transmitter. You have a receiver, means a line receiver, right? When the hole align pass through the pass, then the light can pass through. Then the light will hit the receiver. Once the receiver receives the light, then there's a transition either from a low to high, high to low. Okay, and then when the disk rotates, then you have a series of this transition as output, and the light output is a waveform, right? Here, and here you have a terminology about the pitch angle between two adjacent holes, right? So then you see the pitch angle is equal to what? One full rotation 360 degrees, yes or no? So theta p equal to 360 degrees divided by the number of the hole in the outer ring. That's it. Here. So this is then you can count. Let's say you define a time window theta t. You count the number of pulses you observe, right? If the number of pulses is a c, capital C. So C times theta p is total rotating angle divided by theta t. This is what average angular velocity. Yes or no? Do you understand the equation there? So it's quite straightforward, right? So average angular velocity. So you just need to count the number of the pulse, c times theta t divided by duration. Now you set the timer as an observation window theta t done already. So mathematics is inside there. The physical hardware is there, right? So this slide, as long as you understand how it works, this slide good enough for me. Okay. Then you may want to know how to have a sensor which allows us to measure linear velocity, right? Then your design is like this, right? Same, okay? So then you will have a line emitter, line receiver, right? So you have a vertical strip, okay? You have a transparent and opaque. Transparent means what the light can pass through, right? So when you have a linear motion, okay, linear motion, then the light will pass through, then you have a signal of transition, okay? Here you may see we have a channel A, channel B. This is for us to know direction of the motion. And then you will see, okay, here you see you have a two ring of a hole. Actually, there's an offset of a 90 degree or 25% of the cycle, one period, right? So 25% corresponds to 90 degree. If the full cycle corresponds to 360 degree, then 25, 1/4 of a cycle is a 90 degree. Okay. Then you see the offset between signal from A, signal from B. You see the blue color, green color is offset of 90 degree. So based on this difference, then we know whether it's clockwise rotation, counterclockwise rotation. Okay, so this is for us to know direction of the motion. Okay, and then it's just a simple example for you to know what is the pitch angle. Just now, you see this formula, compute pitch angle. Okay, so you go through this example, then you know how to compute pitch angle. Then from this example, then you know, okay, how to determine based on the count the number of transition from low to high, high to low, and we know the pitch angle, we know the time window for doing the measurement. Then immediately we can compute the average angular velocity. So you see, if you go through this example, then you will know. Okay, this is very, very simple working principle for us to measure angular velocity. Okay, and then okay, so by default, this sensor allow us to measure angular velocity and also direction of the motion, because we have two signal from signal A, signal B, and the difference between signal A and signal B is 90 degree, right? Now you see, we can also make the same sensor, the same design, which enable us to derive the position information, just adding one pair of one hole. We call, you see the signal Z, just adding one extra signal Z, right? So that corresponds to the reference zero position. You remember mathematically, if we have a velocity, integration velocity is what? Integration of velocity is what? Position, yes or no? When you do this integration, you must do integration start from the time 0 to t, right? How to know this zero position? Is this R? You see, you have a one, okay? Here also you see R. Here you see a one, right? So that means the I, okay? You see the I there, okay? Signal I. Sometimes we call signal R, okay? And here is R, right? So that is the position in between. This is the zero position. At this point, you can start to do the integration. Then you can get the position information. All right? Okay. So to know the direction of a motion, you just need to know the phase relationship between signal A, signal B. Right? So this is quite easier. Okay. So this is clockwise rotation. So B will lead A, right? Something like that. Then, in order to know the zero position, you need to have this signal R. Okay, signal R will indicate zero position. Then mathematics involved for us to compute the position is here. So you see, you start with the first two equations. First one, omega bar means equal to C times the theta P. This is the measurement equation now, okay? So you can compute average angular velocity. Mathematically, average angular velocity is equal to theta minus theta I. Theta I means initial position now. Theta is the actual position now, then divide by theta T, right? Then these two equations equal to one is a pure mathematical relationship or definition of average angular velocity. The second one is the equation of doing the measurement computation, right? You equivalent together, you can cancel out the theta T. The time duration you can cancel out, right? Then you have the actual position equal to theta I plus C times the theta P. Theta I is the initial position, but this one we don't know, right? So this one, why we locate when the signal R appear, then we have this theta R equal to theta I. When the signal R appear, remember the count the powers CR, right? CR is when the R signal appear, then the counter's value is CR. You just remember this one, right? Now you have a two equation. You have a theta R equal to theta I plus CR times theta P. On top is theta equal to theta I plus C times theta P. First equation minus second one, then you can cancel the theta I term. The equation on top minus equation below. Okay, theta I is up here. Then you have a theta minus theta R. What is theta R? Theta R is the position at which the R sensor has a signal output. So you treat it as a zero position. So theta minus theta R is an increment from a zero position, right? That gives us the measurement about the absolute position. Okay. This equation for those of you in future, if you are going to play robotic arm in industry, then you will see how come we need to do the homing. That means once you power the robot start to do some movement or something like that. Then after that, they operate. This equation helps you to understand why we need to do so. Because for each joint, robot need to find out each joint you need to find out what is theta R, right? So you see the robot just you need to power, you just do any random movement. Okay, now you understand why all the industrial robot need you to do the homing first before you can use it. Reason is what? For each joint, you will find out this theta R. Basically, you move when the R signal appear, you will remember, I get this theta R down the way. Then another joint will move, find the theta R. Okay, once we memorize all this down the way, then the velocity sensor can serve as a position sensor. Then the robot arm can move in any position already. Okay, so it's magic, but mathematics is this equation. Okay, clear. So, but you go through this exercise, then you will familiar with this equation. Okay, so this exercise help you to understand. Solution is given to you. You just wish to play with it. Okay. Then how to know direction of the motion? Basically, you just need to know okay, signal A, signal B. You don't know their phase relationship. Good enough already. So you can read it. So I'm not going to spend time to talk about all this. Okay. So change of direction motion is quite straightforward, right? Okay. So in future, if you have a microcontroller, you want to do some experiment, you can follow this connection diagram to play. But in case if you do not have a microcontroller, it should be okay. I guess this is for you to know how to do the interface of the microcontroller with a temperature sensor, right? But we will come back to this in lecture 2, right? So, okay. So maybe we take a break of 5 minutes, so then we start at 3:25. Okay, so we, could you ask, our student to come? Okay, so we continue to study the second lecture in session 4. So you remember in lecture 1 of session 4, we have studied 2 examples of analog sensor and one of the 2 examples of analog sensor, digital sensor, right? So the design principle of analog sensor is to convert any physical quantity of the measurement into physical quantity in electric domain. Then lastly, convert physical quantity in electric domain into voltage, right? Then for digital sensor, the principle is to convert any physical quantity of the measurement into a series of pulse, 0, 1, 0, 1. Okay, so we call it as a square with the pulse or digital pulse, right? Then we can use a microcontroller to do the counting. Okay, so based on these 2 different scenarios, okay, so we start with the universal way for us to interface analog sensor into the network of IoT, or how to attach analog sensor inside the digital network, right? So this skill will be useful for you to develop robots as a product or implement automation system in future, right? So this is similar like the study in session 3. You will put yourself into the role of a user of a microcontroller, right? So because we are not asking you to become a designer of a microcontroller, so you now try to switch your mindset from the mindset of a student to learn knowledge into the mindset of a user, okay, with the purpose of making use of a microcontroller. Understand? You need to switch your mindset into the mindset of a user, how to use microcontroller, right? Okay, then you will relax. Otherwise, if you put yourself into the mindset of a student, then you will be stressful down. You say, all this here, how do I remember? As a user, I just quickly go through the slide. What do you know? You need to configure all these register. No need to remember. As long as you know, these are the register, you need to pay attention. Eventually, you need to use it. Okay, so treat all these slide as a dictionary, right? You go through, then you confident, okay? In future, if you want to know exactly how to set the value inside the register, then you can read the detail based on your need, then you decide the value. Clear? So put yourself as a user, right? So don't put yourself as a designer of a microcontroller. Otherwise, you are suffer. Then you see you get lost. Okay, clear? So and okay, this is the roadmap about the detail study, okay, of microcontroller. Let me see in future. I guess only few of you have we knowledge, right, about the microcontroller. Many of you do not have. At least this slide is useful to give you some guideline or give you motivation for you to decide whether you want to study microcontroller or not in future, right? Okay, so and then for the second lecture, we will study the working principle, okay, behind the interface to analog sensor, right? But I will go through the working principle. This is quite straightforward to understand. Once you understand the working principle behind the implementation by all the microcontroller, because this is a universal working principle, right? There's a slightly difference in detail, right? So as long as you understand the working principle, then I will go through the implementation example by ARM Cortex M4, right? So you treat it as an example, right? Treat it as a dictionary. You go through, you know, all these register you need to pay attention. Good enough already. Okay, so and based on the lecture one, you know, in the digital world, we have both analog sensor, digital sensor. In order to develop IoT, it is necessary for us to know how to interface analog sensor, how to interface digital sensor, right? So in lecture two, we focus on the way of doing interface with analog sensor, right? So this video help you to have this idea about the presence of analog sensor in industry. So you look at this video, you will see this is a storage tank genre. And inside the storage tank of the liquid, we need to constantly monitor the liquid level. Okay, in order to see whether this tank is full or is empty or is half full, etc. Then you will see the sensor which measure the liquid level is analog sensor, right? So and eventually they measure the pressure based on the pressure difference, then they compute the liquid level. So this can help you to understand that there are many opportunities for you to encounter the use of analog sensor.
Manufacturing process is continuous. There are operating parameters that change continuously every fraction of a second. These operating parameters are often called as tags. Plant operators monitor and control the process conditions through the process control systems like DCS, SCADA, PLC, etc. The process team monitors the plant operation and performance by calculations and data analysis. Process teams identify the constraints and troubleshoots the plant problems. Process monitoring and analysis is essential for continuous improvement of plant performance. The performance calculations need real-time and historical process data. The performance calculations are also done manually, repeatedly on a regular basis. The process team often sit outside the control room, and they struggle to get these data manually. The historical data is limited to few days due to limitations in process control systems. Process monitoring becomes easy and efficient with NTC view. The process data are collected from process control systems and stored in NTC server. The performance calculations and KPIs are evaluated automatically. InfoView provides analytical tools for converting process data to information and to visualize it. This information is then made available across the organization and across devices. InfoView analytics helps to quickly analyze plant performance with on-the-fly calculations, custom metrics, and self-service analytic capabilities. It accelerates troubleshooting of process issues, which enables quick corrective actions. InfoView further improves the efficiency of process monitoring, reduces the man-hours for data collection, calculations, and analysis, and eliminates the errors in data collected. Within InfoView, the process information is available everywhere. InfoView supports self-service and single-point configuration. A group of text configured to visualize certain process information is called the viewer analysis. The views configured in one device are available on all the other devices and applications like PCs, mobiles, tablets, office apps, and even on Google spreadsheets. Insys InfoView remotely helps to stay connected with the plant while away or on the way. All of these are optimized for screen and enhanced for touch. Search, analyze, save and share the information just like web version.
Okay, so this is a typical example of you to deploy IoT in industry. So the previous video actually is an industry in chemical manufacturing. You see the first picture you see is a refinery plant, right? So inside the refinery plant, you have a lot of storage tank, right, of the liquid. Then it pass through a lot of chemical process to transform input material, okay, in the form of liquid into liquid of different chemical property. This is not like mechanical manufacturing. Remember, mechanical manufacturing is for us to transform to a matrix, right? But for chemical manufacturing, the main objective is to transform the property of input material, right? So then we need to monitor all the chemical process, collect all the data. So you mentioned process monitoring, right? So you have a massive network of IoT to collect all the data. Then people stay inside the control room, analyze the data, visualize the data, then understand the operation, whether the process is in control or out of control, something like that, right? So that is a typical scenario for you to see application of IoT in chemical manufacturing, all right? But come back to our robot, you see, and even for robot, we may face a situation of making use of analog sensor, okay, to do the measurement, right? So robot and info are yeah, just quickly go through. So depends on the use of sensor, and if they say inside a production line, inside any machine, you want to implement a control system. Once you have an analog sensor, normally your controller is a digital device. Then automatically you must know how to interface analog sensor with a digital controller, right? So then, okay, you need to know whether what is the working principle built into any microcontroller. Okay, so in order to understand the built-in working principle of interface to analog sensor, first you need to know how to do digital to analog conversion. Why you need to do this? The reason is because this conversion is very easier for us to achieve, very cheap. Then analog to digital converter will make use of this one to achieve analog to digital conversion. Understand the reason? Because this is a very cheap solution. Then leverage on the use of this solution to implement cheap solution for analog to digital conversion, right? But of course, we can have dedicated analog to digital conversion circuit, but that one will be very expensive, right? So this is why all the microcontroller has built-in solution, which is build on top of this conversion. Okay, so first look at the digital to analog conversion. For example, I have a digital number. How to convert this digital number into analog to voltage, right? So good news to you is we have a lot of ready circuit for you to achieve. This is a very simple example, help you to know that it is very easier, very cheap for us to achieve digital to analog conversion. Okay, for example, this is a case with an input of a digital number which has only 3 bits. You see, bit 0, bit 1, bit 2. That means analog number is 0 all the way to 8, right? And through this diagram is very easy algebra. When bit 0 is 1, that means we have a 5 volt, V3 equal to 5. When the bit 0 equal to 0, then V3 equal to 0. You remember, digital number 0 means 0 volt. Digital number 1 means 5 volt. Okay, right? So when bit 1 equal to 1 means V2 equal to 5. Bit 1 equal to 0, then V2 equal to 0. Okay, so you can easily write down now. You see the voltage and the operational amplifier. You know the property of operational amplifier. The input voltage difference is almost 0. You see, one end connected to ground, That means the voltage on top is also 0 volt. So you can easily verify the output voltage is negative regular V1 plus V2 divided by 2 plus V3 divided by 4. Right? So that means in a fraction of a second, once the bit 0, 1, 2 appear at the input, instantly you get analog number. Okay, so this is for you to know. And then if you want to know, let's say I have a 1 bar, how to obtain the voltage which corresponds to 1 bar or 2 bar, 3 bar. If you are going to know how to convert 1 bar into analog value, then 2 bar, 3 bar, you just stack them together. It's not an issue. Okay, but this is a very, very interesting circuit. Okay, you can easily prove that the relationship is like this, right? Then how to prove? You need to apply this concept. You remember when we study control theory, we have this multiple input, multiple output equal to the sum of a single input, single output. For this one, you see, you can treat it also as a multiple input, single output. It is equal to the sum of a single input, single output. So it means when you consider P0 is an input, then you ignore P1, P2, the rest. When you consider P1 is an input, ignore the other. Then you add them together. So you can easily find out the relationship. Understand? So you must apply this principle in order to prove this relationship. Okay, so it's a sum of a single input, single output. Each bit you treat as a single input, independent. Right, so then you can easily prove this relationship. So it's very, very interesting. Okay, then based on this digital to analog conversion, we can come up with these two specifications about the resolution. Okay, for example, how many analog voltage per unit bit? This is the digital resolution. This is one bit of input digital number. Then we produce how many voltage as output, right? So this is the analog voltage per unit bit, or reversely, each voltage 1 volt of output will correspond to how many volt, the value range of the digital number, and the digital range, okay, 1 volt per unit volt output, which will correspond to how many variation of the input digital number, right? So this give you basically tell you the sensitivity, right? So output vary 1 volt, then the input must vary how many number, or if input vary 1 digit, then output will vary how many voltage. This is a sensitivity, right? Just help you to measure sensitivity. That's it. So you can play this small exercise, then you understand what we mean by that. Okay. So you see, digital to analog conversion very, very simple, right? We have a very fast circuit. Now the question is how to make use of the PA conversion to achieve this is a need. What we need is this one. We have a voltage as an input. How to convert this voltage into digital number, right? This is what we need. How to leverage of the chip circuit, right? So then this is a solution. We will use EAC, but we must pay attention, right? Try not to think in this way. The input is fixed voltage, never change. You must consider this scenario like really a bit of complication. If you say your input voltage is a function of time, understand what I'm saying? Then how to do the conversion to convert a time function of analog value into a time function of a digital number? Think in this scenario, then you will focus your study. Otherwise, you may say very simple. You have only one voltage, one analog value convert into one digital number. This is very simple, right? But if you think in that scenario, it's too simple. But in general, we may have a requirement of converting time function of analog value, because the sensor can do continuously measurement, then output time function. then how to obtain time function of digital number, right? So then you will see to do this conversion, there are two steps. One we call is jumping, to take the jumper, that means to make the continuous time to become a discrete time. Second operation is quantization. You need to familiarize with this two terminology, otherwise you will get lost. Okay, jumping means take the discrete jumper from a continuous time function, right? Quantization means for each number convert it into digital number. Understand? You sync these two processes, then you can easily follow the description. Then for each number, see quantization, convert into digital number. Please get the allocation number. Once you get the number, you can do encoding, and you can send the store inside your computer.
Analog to digital converter is a device whose input is in analog form and output is in digital form.
Jumping
It converts analog to digital by a pulse code modulation method where first stage is sampling, second is quantization, third is binary encoding. Analog to digital converter, ADC. Analog quantity may be voltage, temperature, sound, speed, audio, etc. It is information or signal. Digital means it is in binary form, 1 and 0, 1 means on and 0 means off. Converter is a device. Analog to digital converter, ADC, is used for converting analog signal into digital form. Most of the data is in analog form, but most data processing is done using digital computers. So for processing and / or modifying signals, we need to convert it in digital form. Pulse code modulation, PCM, technique method is used to digitally represent discrete analog signal. PCM consists of 3 stages. 1 is sampling, second is quantization, and third is binary encoding. The sampling measures the amplitude of the signal at different intervals. Quantization is the process of converting the sampled continuous large set of input value to small countable discrete value. Binary encoding is assigning a binary equivalent to each state of output. There are 4 types of ADC. 1 is counter type, second is integrating or dual scope, third is parallel or flash, fourth is successive approximation. Examples of analog to digital, A to D, converters are microphone, converts analog audio signal to digital form, voltmeter, converts analog voltage signal into digital, scanner and camera, converts analog image into digital form, digital speedometer, converts analog speed into digital form, etc.
Okay, so the video actually summarizes the key procedure. The first two, because the last one to do the encoding just packs the digital number, either binary number or hexadecimal format is not important, right? So important thing to remember is to sampling, quantization. Because later when we look at the implementation of this principle, then you will see the similar terminology there, right? So you have a device which will do sampling, you will have a device which will do quantization. So you must have 2 different devices to handle this 2 operation. Sampling means to make the continuous time signal to become a discrete time signal. So you take the sample of the signal at the discrete time. Then for each sample is analog value data. They must convert it into digital number. That's it. Think this way, then you will be comfortable. Otherwise, you will get lost. Okay. So you see on top you have a continuous signal in time. Then it become a discrete signal in time. But still we are analog in value. Remember terminology, okay? Discrete signal in time, but analog in value. Okay, each number is analog value. Okay. Then second step, you need to do quantization, right? Then you will obtain a time function of the digital number, discrete in time, also digital in value, right? So this is an example of using 3-bit, 3-bit, then you have A level, right? 3-bit, then you see 111, 110. But this just illustration. In practice, you can have 16-bit, right? Then you have a lot of level of 65,556, right? Okay, so this is just for you to know. And okay, once you understand, you need to do these two things. Okay, next is how to convert. Okay, to do jumping is very simple. Jumping is like you just switch on, take a jumper, right? You copy this signal, right? You just switch. You see the switch S one. Okay, switch. It's very simple. Just okay, periodically read the analog signal. Okay, complicated is how to do quantization. Quantization is analog to digital conversion, right? So you see when you see ABC. But inside the name, you never mention jumping. So implicitly, person to do is jumping. Then you have a lot of jumper. Second thing is to do the ABC. Now you look at this diagram. This diagram makes use of DAC. Do you see inside you have DAC, digital to analog? This is the basic principle of the philosophy is what? Philosophy is a prediction verification. That means I need to know what is the digital number correspond to this analog value. I just predict I predict start from 0 all the way to maximum digital number. Understand the working principle? I predict 0, 1, 2, 3, or then 65,000, something like that. For each prediction, you have a digital number. Then I use DAC, convert the digital number back to analog, then do comparison. If my prediction is correct, means what? After DA conversion, I will get analog value is exactly equal to input analog value, yes or no? When they match, then you have a comparator there. Then this will make a transition to stop the prediction. I predict from 0, 1, 2, 3. Once I reach value, it match this one, then the signal appears stop prediction. Then that number is output. Understand the working principle? Prediction, verification, once you match, then stop. But the thing is, when this counter runs at a high speed, 1 million or 80 million prediction per second, then you do not see in a fraction of a second down the line. Okay, so this is a working principle. So prediction, verification, then there is a we call comparator. Once you match, make a generate signal to stop the counter. Okay, so this is a working principle. Then once you apply this, you can convert this voice into digital voice. You say you have the microphone, output from microphone, you see is a time function of voltage. Then you see here, you take a jumper. Once you get the one jumper, you do the conversion quantization. Then you have a series of digital number, right? Okay, so and this is in the video you mentioned image. Even for the camera, it's the same. But this is a very easy illustrative. It's a camera. This is a camera, color camera with only 4:1, 2x2 resolution. Now you see it's very low, 2x2, right? Then you see output from all these image sensor analog signal in time. So you see the quantization, jumping quantization. Same. This is the way you understand how to obtain digital image. So something's happened like this. Okay, you increase the resolution. This is what you have inside the handphone. All right, clear. And this is an example of image with the resolution 100 times 100, 100, 100. All right. Okay. So you see, you have a lot of ADC. You see, you have 16 ADC, right? So you do the conversion. So for ADC, it's the same. We need to know sensitivity, right? So that one digit change, what is the corresponding analog voltage, or one voltage, what is corresponding variation in digital number. These are the sensitivity about the converter, right? And it's just a small exercise for you to go through. Okay, from this example, immediately understand for Cortex M4, the input voltage range is always fixed from 0 to 3.3. This is something special. Because for other microcontroller, it could be 0 to 5 or it's up to you, you can choose the input voltage range. For this one, it's always fixed from 0 to 3.3. If your actual input range is not like this, you need to have a network of resistor to scale it down or scale it up to this range. It's quite easier, okay? How to step down the voltage range? Then you put the series of resistor, right? How to step up? Then you need the amplifier, okay? So this is not issue, right? So in practice, you can have a circuit to scale up, scale down the actual range of voltage variation to match this required range 0 to 3.3. And ARM Cortex M4, the digital number is 12-bit. Pay attention. ARM Cortex is a 32-bit microcontroller. So everything inside there is 32-bit. But once you do the conversion, because due to the low cost, so it will not offer you 32-bit. So for the range of digital number, it only offer you 12-bit. So you only have a 12-bit. It should be good enough for many applications. So you have okay. So this just for you to know. And okay, so that is a working principle of interfacing analog sensor into digital microcontroller inside IoT. You remember, you just need to do two things. Once you have an analog sensor, if you use ARM Cortex M4, first thing to do is what? To scale up or scale down the voltage within the range of 0 to 3.3. Second is to know to use the built-in function of ARM Cortex M4. Then you will see for the built-in ADC, it will allow you to configure jumping. Always remember, first is to do jumping. Make the time continuous function to become a time discrete function. Right? Second one is quantization. Convert each number into analog or into digital number. Let's say, right? So ARM Cortex M4 has a built-in solution. Then, as long as you understand the working principle in the previous slide, then we just focus on how to use the built-in solution. So put your mindset into the mindset of user, right? So, okay, why do we use microcontroller? In our context, is IoT, right? Because you get network sensor, network actuator, okay? So your role is user, always remember. And if you want to know the full detail about the microcontroller, then you need to study okay, all these details, etc. And as a user, you just need to know how to configure the built-in hardware and how to monitor the functioning operation of the built-in hardware, right? Then how to read the data, write the data, etc. Right? But in terms of assembly language, it just move. So you just need to know what should be the value right into what register. Okay. So the remaining slide actually as a dictionary. No need to remember. If you say you need to remember all the rest, then you will suffer, right? Just go through roughly. If I want to do this, I need to use this register, etc. Okay, and you remember, okay, in section 3, I already tell you. For our student, they will spend one semester to study the use of ARM Cortex M4. And our students also suffer a little bit the use of ARM Cortex M4. Reason is what? Reason is I already mentioned to you. The cost of ARM Cortex M4 is extremely cheap, but the performance of ARM Cortex M4 is extremely high. It's like you pay the price of a bicycle, you get a sport car, right? The student get lost. How come I just pay so little bit of money? It's less than $50. Then how come this guy is so powerful? You get lost, something like that. Okay, so you must put yourself in the mindset of the user. In case if you want to move slowly, you always drive your sport car like with a low speed, yes or no? No need to drive a car 2,200 kilometers per hour, right? So you look at this guy, this one has a jumping device, has a two quantization device with such a low cost. Then suddenly you get lots of it. You say, why not just give me one jumping device and the one quantization device? Then my life is easier because I only take care of one sensor. But you see one node of ARM Cortex M4, and now you will attach how many sensors? 12 analog sensor. Now you imagine you can construct three-dimensional network IoT, three-dimensional IoT with asynchronous serial communication. Understand? For each node with this low cost ARM Cortex M4, you can attach 12 analog sensor. Now you get lost already, or so many, because you can attach 12 as a user, you must have, okay, where is the sensor number 1, where is sensor number 2, that create complication, right? And since we allow you to attach 12 sensor, they ask this sensor, why not offer me 12 jumping device, making my life easier. Sensor 1 go to jumping device 1, sensor 2 go to jumping device 2. Make my life easier, yes or no? But because of a low cost, you do not have a 12 jumping device, you only have how many? 8. Okay, remember all this number. 12 sensor at the input, you only have an 8 jumping device. Then you may say, since I have an 8 jumping device, or give me 8 quantization device. Actually, do not have. How many do you have? 2. Now you remember this number 12, 8, 2. It means what? All the jumping device must be shared among 12 sensors in the worst case, right? Yes or no? And the 2 quantization device must be shared among the 8 jumping device. Yes or no? Okay, is this sharing make your life as a user difficult? Understand? Clear? So treat this as a sport car. Also, you like to drive a bicycle. Understand? So you pay a price on bicycle, then people deliver a sport car to you, then you get lost. Understand? You must have this kind of mindset. Once you think in this way, then you will not be frustrated. Right? It's so powerful. You have a 12 sensor. Sometimes you may say, I just need one sensor, one jumping device, one quantization device. Then suddenly you get so many, right? Okay, make your life difficult. Okay, clear? Okay, another complication is, okay, always remember, this general purpose microcontroller is not just only for IoT. But even for IoT, you can do the monitoring, critical parameter monitoring. When you do the critical parameter monitoring, do you know you have a risk requirement for each critical parameter, you always set the upper limit, yes or no? Lower limit, or no? Once this exceed upper limit, go below lower limit, do you want this not to trigger alarm automatically? Yes or no? Even I want to monitor temperature in one particular location. If the temperature go beyond 100 degrees, trigger alarm. If the temperature go below 0 degrees, trigger alarm. Yes or no? Do you have such application? Many, yes or no? This we call process monitoring, right? So this guy is has a built-in support for each sensor. You can set the upper limit, lower limit built-in for you. That create a little bit complicated. You see, A is the comparator. You remember you have an A jumping device. Each jumping device will give you a pair of they call comparator for you to set the upper limit, lower limit. If how we will do the comparison, if the value from the sensor go beyond upper limit, go below lower limit, automatically trigger independent signal. Understand? So it's like a sport car, okay? It's not bicycle, right? But you pay a price of bicycle, you get a sport car, right? Okay. So remember this number 12 input analog sensor. And A sampling device, you see 2 times 4 is A term. Always A grouped into 2. That means for each quantization device, he has a 4 sampling device. Since you have a 2 quantization device, that is 2 times 4, right? Here, okay. So this slide help you to understand this, okay? And then, okay, the good news to you is you may have a single sensor, and you can double the resolution of doing the sampling, because one quantization device, actually you can say you can take one series of sample, another one take another series of sample. If these 2 series you offset a little bit, actually you double the number of discrete sample channels. If we say quantization device, first one take 100 samples, second one another 100 samples. Then you have a 200 sample channel. But this 200 sample can come from one sensor. It is equivalent to say that for this sensor I have a 200 sample. Then I double the resolution, right? Clear? So this is explained by this. So that way, it's a bit complication for you to use this built-in solution. Okay, so this help you to know that you have a comparator. So each ADC, you have 2 ADC has an A comparator, right? Why A? Because you have in total A the sampling device, right? So comparator is for you to compare with upper limit, lower limit, clear? Okay, and since you have now you see the 12A2, see the number 12A, okay? Then you need, as a user, you need to tell sensor 1 go to which sampling device, go to which quantization device. Sensor 2 go to which sampling device, which quantization device. Okay, because it's not one-to-one. So you have a flexibility, so you must tell. Okay, so something like that. And another thing is for the sampling device 0, he has a buffer. That means he can one sampling device, internally you can take A sample and store inside. You see, it's even more powerful channel, not just one, right? Okay, so this is just for you to know. Okay, and okay, this is the upper limit, lower limit. So for each sampling device has a built-in upper limit, lower limit, trigger alarm. You see, this is for the monitoring of a typical parameter like temperature, humidity, right? Something like that. Okay, clear. So then this is the blueprint. You just need to, for those of you with an electronic background, you can take a look. Otherwise, you know that, okay? You can throw in 12 sensor. Inside you have an A sampling device, and inside you have 2 quantization device going up already, right? And here, if let's say you have a 12 sensor, how to physically connect the sensor to the microcontroller? Then you use this table to know the connection key. First column you see analog in AIN0. AIN is analog input 0, right? Analog input 0 all the way to analog input 11 means what? 12 sensors input, right? Clear? Okay. And okay, this one is for you to verify by default maximum capability is 12 sensor, A sampling device, 2 quantization device. Some user may ask the manufacturer don't give me so many sampling device. You can have a reduced capability, special request. And if this company sell the second-hand microcontroller to you, then you need to verify, okay, for the second-hand microcontroller purchased by you, what is the actual capability you can, by reading this register, you know what is the actual number of sampling device, number of quantization device, etc. Okay, this is just to verify, okay, what is the actual capability. And just like I mentioned, for this one, the input standard range is always fixed, 0 to 3.3. Okay, then you need to scale up, scale down. And the output is 12 bit is the number, then this you have this relationship. So you have an input voltage running from 0 to 3.3. Output is the number from 0, 0, 0, 0, if you use hexadecimal all the way to FFF. Okay, this is 3 digit in hexadecimal. Each digit has a 4 bit. 3 times 4 is 12 bit. This is why you see maximum number is what? FFF. F means what? 15. Okay, yeah. So you can easily verify this one. This guy has a built-in temperature sensor, right? So you can use a built-in sensor to do a test of conversion, to read what is the actual temperature of your microcontroller of this node. So this is very useful, right? Okay, so this is and how to use this is the same procedure. First, you need to configure the built-in solution. Configure means what you tell where is your sensor? We use 1 sensor, 2 sensor, or 12 sensor, or sometimes you may use sensor in pair or whatever, right? And sensor 1 must go to which sampling device. Okay, then after sampling, you go to which quantization device, right? So you need to know that whether you want to set the upper limit or not, right? Clear. So once you know the background knowledge, then you can get out as how to configure this guy, right? Okay, configure input. So you see, you must once you do the physical connection, you must tell where are these sensor. Whether you attach 1 sensor, 2 sensor, 5 sensor, or 12 sensor, right? So you must write the number here, right? So and you follow the instruction, you will tell you, okay, so follow this. That means you through use of this register, you tell how many sensor actually you attach to this not maximum 12 sensor. Okay, so this is for you to know. And among all these 12 sensor, eventually you can decide whether I want to do analog to digital conversion, right? Maybe some sensor may not use it, right? Depends on the application. So you will turn on all these ADC. Okay, once you turn on means the voltage you will be input. Okay, you see you will enable. So okay, ADC enable. So detail you read the instruction, right? Okay, and reference voltage actually just turn on because you just set the 1 lastly to be 1 means it's always 3.3, right? Okay, not much. Okay, here is for you to do. So you see, this register divided all the bits into bit divided into how many group? A group, John. Each group is a selection. Let's say for sampling device 0, it will pick up the which sensor. You have 12 sensor. So each group you have the 4 bit allow you to generate number from 0 to 15. So you cover 12. So this is to assign, to decide. For example, sampling device number 1, it will get the data analog voltage from which sensor. Because you have 12 sensors, always remember 12A2. Then for each sampling device, you must select among the 12 which one. Then you write this. You see, group multiplex 0 means the sampling device 0 will take which sensor from out of this 12. Okay, so this is the way for you to choose, right? Okay, and okay, this is for you to know. Okay, but for ADs, IoT may not be so important. If let's say you use this to implement feedback control system, feedback control loop, and then you can use motor signal to trigger analog to digital conversion, right? So you see, you have a lot of external signal to trigger conversion. So here you decide. Now you see you have a 4 group because each ADC have a 4 sampling device, another ADC another 4. So immediately you know you must have 2 this kind of a register. 1 for ADC 0, another ADC 1. Each ADC has a 4 sampling device, right? So it will trigger external signal will trigger automatically do the sampling, right? Okay, so this just for you to know. And then for each ADC, you have a four sampling device. In case if you choose motor signal, tomorrow we will study PWM motor, right? So normally we will implement motion controller. Motion control means the controller will control motor. Then the motor will output PWM signal to trigger sensory feedback. So this is for this one. You see, if this is the triggering signal come from the motor, then because tomorrow you will see even for motor in the cell, you have two group of PWM. So whether it's from group 0 or group 1. Okay, so that means this one must relate to motor study, right? How to interface with the motor. Then you will know, okay, PWM can also group into two groups, right? Internal process, choose the sampling type frequency of clock. So just follow here, you can select the frequency of doing the sampling, etc. Right? And here also you specify how many conversion per second you can do. Now you can see the speed. Maximum speed is what you look at here. You look at 0.7. 0.7 means what? You can do 1 million conversion per second. 1 million conversion per second is why it's a lot, very fast. Okay, so this gives you confidence about the speed. 1 million per second means to convert one is a fraction of a second, not 1 nanosecond. Good enough. Okay, so okay, this is then this one is configured sampling device 0. You see, first sampling device can have pick a sample, store internally, buffer, right? Then for each one, then you see all these 32-bit divided into a group. Each group just specify, determine one sample, right? So you can read about, let's say TS0, IE, enable, interrupt. Is it the last one? N0 and D0 is a differential, I guess. Whether you want to do the to convert the difference between two sensors, because you have a 12 sensor, 12 sensor will form 6 parallel, yes or no? 6 parallel. Instead of convert absolute value of two sensors in a pair, you just do the conversion of the difference between these two sensors. And in industry, you will see a lot of application. You remember the bridge circuit. You have a bridge circuit like the core resistor, and then in between you have a voltage in the left-hand side, voltage in the right-hand side. I just to monitor the difference between the voltage in the left-hand side, right-hand side. If they are equal, nothing happens. If they are not equal, that means something happens. Now you see, with this, you see the support. I just convert difference between two voltage. This is B is means here, right? Okay, you see. 0, 1 is 1, 2, 3 is another pair, 10, 11, another pair. That means these 12 sensors form a 6 pair, right? And I already draw the circuit here. You see, this is very, very popular circuit to convert resistor into voltage. Then you just compute the difference of voltage, right? Okay, so this is a typical application, right? And this is a activate, right? And BZD is to indicate to you, and the hardware is doing conversion, right? And the last 4 bit, because each ADC has a 4 sampling devices. Whether you turn on them all together or just turn on one. If there's one sensor, just on one. If you on all the sensors, you put all these bits to be one, turn on them. Okay, something like that. Okay, so detail you read, you treat all these as a dictionary. Among the 4, you can also define the priority. Okay, which one comes first, followed by another one. You see, that is really looks like it's a sport car, right? It's not like a bicycle term. So you can define priority by yourself. Okay, so this is to in case for your application double the resolution. That means input is one sensor. Then you use these 2 quantization device to do the conversion of a value come from the same sensor, right? So when you do the sampling, if you make the difference offset is 180 degrees, create this offset. Then first ADC, let's take 100 sample, second one take another 100 sample. Even together means what? You have a 200 sample, right? Just now I mentioned maximum speed is what? 1 million per second. With this arrangement, 100 degree offset, they can achieve 2 million per second. Understand? This is a double the number of sample. Okay, you see the offset between these two it's up to you to control, but you choose a special value like 100 degree, right? So it's 100 degree, then you just offset, then you double the sampling. Okay, 100 degree, choose this one, you double the number of sample. Okay. Okay, this is for you to know how to set the upper limit, lower limit. You see, for one register, COM1 is upper limit, COM0 is the lower limit. That's it, right? So you have a sampling device. Each one has this has upper limit, lower limit, right? So hardware will help you to do the comparison and send the alarm. When go beyond upper limit, go beyond lower limit, trigger alarm, right? Okay. And how to trigger alarm, you can also tell the system whether always trigger alarm or just trigger once. Then you follow this explanation, right? Even go below the low limit, how to trigger alarm, okay, etc. Right? It's very powerful, right? Okay, and once you trigger alarm, when you do comparison, always remember to reset. Otherwise, your CPU always take care of internal signal interrupt. Okay, so this is how to once you do the service response to the alarm triggered by the computer. Always remember to reset it. It's like during the study in section 3, right? When you are hungry, your stomach tell your brain, then you go to restaurant to eat, your brain will reset this internal signal. Otherwise, you keep eating, right, until you die, right? So this is the same situation, okay? When you respond to an internal signal, always remember to reset it after you take action according to internal signal, right? Okay. So, okay, for all the digital comparator, you can also mix up the order. It's not sampling device 1, use comparator 1, device 2, comparator 2. It's not like this. You can also mix how to select, use this register, right? So it's like sampling device 1, select which comparator. You can mix up, right? Okay. So like if you need a bit more flexibility, right? Okay. Yeah. Then okay, this is just for you to know. Okay. For because you have a sampling device, whether the output of a sampling device after digitization will go to the comparator. You remember, you go to comparator means you must set upper limit, lower limit, your trigger alarm. If you do not do this monitoring, then go where? Go to P4. You see buffer, yellow one, right? So you must decide whether to go to comparator or go to buffer. Is all this bit indicate, right? So okay, so you see you need to tell, right? Okay. And the rest, I guess, okay, this is turn on, start to do the jumping, etc. You set the bit you want, then the hardware will start to operate. Then output, this is another additional feature. You can do the filtering, remove the white noise, right? So, and how many, after digitization, how many number you can add them together, compute average, then it becomes the actual output, okay? So it's a built-in operation to filter out the white noise, okay? How many digital number to do the average up to 64, you see, look at here. You can add the 64 digital number together, compute average as an actual output, okay? So then this is a mask interval. Some internal signal you do not pay attention, you can mask them out, right? Then run them, okay? Run means once you run, basically just read the digital data, where to read. So it's from this register. That's why I mentioned analog value convert to 12 bit is verified here. Look at this data. Bit 0 and here bit 11 is a 12 bit, right? So you read the number from here, right? Etc. And in case if you read slowly, all the data is inside the buffer. You can still retrieve intermediate data inside the buffer. So you have an indicator to the head of the buffer, tail of the buffer, based on this number that you know here, how to retrieve all the data, etc. Okay, clear. I guess the rest is to output the interrupt. Also, you must start that you can still verify whether interrupt appear or not, etc. Right? So interrupt means the internal status. Let's say you use a digital comparator to trigger, okay, alarm and go beyond upper limit or limit. You can verify here. You have a comparator, right? So always we tell you, okay. So what happens if you go beyond upper limit, lower limit or not? Then how to clear the interrupt is just telling you write the one to clear the interrupt, okay, in case you handle, right? And since you have a buffer, once you the output go to the buffer, if there's an overflow of the buffer, that means you never read, then the data exits the buffer, then hardware will also tell you this overflow, right? Okay, you lost something else, right? Something like that. Okay, so that's about the interface with analog sensor. So conceptually, it's very simple, and the way you use it is because this guy is so powerful. Because we have a 12 sensor input, internally we offer you a sampling device plus 2 quantization device, and also they offer you a pair of a comparator to do hardware-based monitoring. Okay, whether it's the sensor output is within upper limit, lower limit, or beyond upper limit, lower limit. That may be your operation to configure these solutions like we communicated, right? Okay, so we move on to look at how to interface digital sensor to IoT. But this one should be easier because you remember digital sensor, okay, is either you have a pulse. Okay, always think another scenario of a digital sensor. Your sensor eventually has a built-in microcontroller. Then your microcontroller can output digital number. Then you must treat the sensor as an extra node. You remember when we started section 3, 2 nodes can communicate data as a series of bit. Understand? So with a synchronous serial communication, you can connect to 4 neighboring nodes. With asynchronous serial communication, you can communicate with 6 to 8 neighboring nodes. Then you build up a 2-dimensional IoT or 3-dimensional IoT. For digital sensor, 2 scenarios. One is it directly output series of waveform. This is one scenario. Or you have a smart sensor already, and the sensor itself has a microcontroller inside. Then in that case, you treat it as a node. Then communicate with the node inside the IoT. Then you use synchronous serial communication or asynchronous serial communication. Right? So these are the 2 scenarios. Okay. So, but here we just talk about the second situation. I mean, the sensor itself output a pulse waveform, right? Because this is a popular scenario in robotics, in automation, right? Like the optical encoder. Okay. So then Cortex-M4 has a built-in support for this solution, right? So it's easier. But in this case, it's very simple. It just offers you two examples. That is not very complicated. You do not need to know which one to do which one. Okay. So this one maybe is quite clear, okay, to study. So application, okay, just I mentioned you have 2 types of digital sensor, right? So one output digital value. So it's this one. That means with the sensor itself has a built-in microcontroller, right? or the one output pulse, the square waveform. And that is what we know for inside the robot is a pulse waveform. Okay, so these are the two scenarios. And here we only focus on the scenario in which the sensor output square waveform, right? Okay, and you have seen this video. You see, this kind of control basically make use of something it's very easier. And you see in robotics, okay, you do the human robot interaction, right? So how come robot can perform a motion? Because there is a sensor level of feedback control, right? Okay, so this should be good enough now, right? And okay, I just played a little bit of this video. You see robotic arm, and you can perform a very complicated motion. How come robot can perform a motion? It means what? You have a feedback control loop. So inside feedback control loop, you have a digital sensor. Then you must have capability to interface with the built-in. You see this robotic arm has a digital sensor inside, right? Okay, but this is an example showing you okay, I help you to understand it is not a big deal for machine to outperform human being, right? You see, this person is a champion in Europe, right? So you will see it's very easier for robotic arm to win the match. Okay, so good enough now, right? So then, you see your arm. You need to have a sensor there, okay? And even for the AGV, right? So autonomous vehicle, right? To control the field velocity. You see, all these are embedded mobile vehicle, right? So all the control must be very, very precise. Yeah, okay. So I just played it a bit so just for you to know. Okay, okay, yeah. Okay, so then we want to know how to interface, right? The sensor with okay inside the microcontroller in IoT. Okay, and what is the motion? Is just for you to know. Okay, so in order to control motion in automation line, motion inside the robot, and I guess from the study in session 1, you know, so inside the robot we have a motion control room. Okay, depends on the number of people you have written, so you have a multiple room inside the robot, etc. Right? And in lecture 1 of today's session, you know this is a very popular digital sensor in robotics. Okay, and in particular for rotary motion or angular motion, we have angular optical encoder, right? Okay, and from this type of design of a sensor, you immediately understand this sensor outputs 3 signals, yes or no? Signal A, signal B, signal R. Okay, why do we need the 3 signals? First, we need to measure absolute value of velocity. Second, we need to know direction of the motion, clockwise, counterclockwise, forward or backward, right? So one is what? We want to make this sensor to behave like a position sensor. This is why we need to do integration of the velocity to obtain position information. This is why output from this sensor are 3 signals. Right? Immediately, you know, for the ARM cortex, he must have a module which will take the 3 signals as an input. You can easily guess out that, right? So then, okay, so I can skip all this slide. And okay, this is the way for you to configure the built-in solution inside ARM cortex, etc. All right. Then for this one, it is not so generous, but it should be good enough already. Right? You see how many in the digital interface to digital sensor, you see two, very simple, right? So, but with the two, it should be good enough for you to implement a car-like vehicle, yes or no? For a car-like vehicle, either you have a one degree of freedom for the control of the speed, yes or no? Another one is steering. Good enough already, right? So that means with one is very low cost, $50. You have a hardware support to control your autonomous vehicle. Come already. Yes or no? One for velocity, another for steering. In case you have a differential drive vehicle, what is differential drive vehicle? Control left velocity, right velocity. If these two velocity are the same, they move together a straight line. If the right hand side faster than the left hand side, then turn left, right? So that means what? Regardless what is the working principle of your vehicle, one is good enough, very cheap, right? Clear. Since you only have a two, then inside it's not complicated, just one by one, right? So you have a one digital sensor connect to one mixer. There's no multiplexer. So you can attach only two digital sensor to this hardware support. So it's very easy. So you see, he has a built-in position integrator. He has obviously this is a velocity sensor, right? And you can tell you direction. He can take in a 3 signal as an input. Okay, this is a connection diagram. You see, you have a phase A, signal B, plus reference signal, right? And this one give you more flexibility. Okay, signal A by default is positive pulse. In case if your sensor output negative pulse, you can also handle it to invert internally, invert your pulse, right? Okay, so this is just for you to know. And look at the diagram, it's very, very simple. You see, you have a phase A, phase B, IDX. IDX is a signal R, reference signal to indicate zero position. Now you see input signal 3 are there, yes or no? A, B, X. X means R or I, right? And another thing is, this guy has a velocity pre-divider. Pre-divider means what? If your motor is high speed and you set the pre-divider, you slow it down from then you can still handle the interface with a high-speed motor. Understand? So this is the advantage. So inside you have a velocity accumulator, see on the position integrator, everything is there, and velocity timer, and inside you have a QEI load. Okay, everything is there. But pay attention. The formula you remember in lecture 1. The formula is what to compute average velocity. C is a counter. You count how many, it's a time window, how many hours you count, right? Theta T is a time window of a measurement, it's a value inside the low register. Theta P is what? It's a pitch angle of your sensor. Then you can ask yourself, will the manufacturer of the microcontroller know the parameter theta P of a manufacturer of sensor? Answer is yes or no. The answer is no, right? So it means what? Whatever you read from this microcontroller actually is a C divided by theta P. Once you get the C divided by theta P, based on the sensor you use, you must read the data from your digital sensor. What is the theta P? Then you must do a multiplication of theta P times this, then you get the actual angular velocity. Pay attention to this, right? Because microcontroller manufacturer may not know the sensor manufacturer. Okay, clear? Okay, and then since you can connect 2 digital sensors, each sensor will output 3 signals. In total, you have 6 signals. Now you see the connection diagram is here. 6 lines connect to each pin. You follow this table, you know how to do the connection. Done already, right? And clockwise rotation, counterclockwise rotation. So this is a working principle. But anyway, ARM Cortex M4 will have built-in this. You will follow this convention, right? So then change direction of motion. So as a user, you just need to know how to configure it, then run it manually, right? Okay, to configure input, you need to determine the time window to observe the measurement of data T, so data T is equal to the value you roll times the divided by frequency. 1 over frequency is what is the duration of each 6 clock? 1 over frequency means what? Duration of each cycle of a system clock, right? So if you roll a number of 100 clock, okay, 1 clock is equal to 1 over frequency duration. The total duration is what? 100 times 1 over frequency. You can easily verify that. Okay, so frequency is the frequency of the microcontroller, right? Then 1 over frequency means what? Duration of a 1 clock cycle, 1 cycle of clock. Okay, if I roll a number of 100 or 1,000, 1,000 times the duration of 1 cycle is equal to what? Observation time, right? Data T. Clear? So then this will just write this number here. It's up to you to decide. So normally is you use this equation to compute the low value. Because I only observe 10 milliseconds. So 10 milliseconds times frequency of the microcontroller to get the number low. We write into here. Okay. So then in the process is to configure all these, okay, whether you want to enable it or not, right? And enable velocity, but you need to read all the detail. What is a velocity divider? Just now I mentioned, is here. You have a velocity pre-divider. And your motor already the high speed and how to slow it down to do the counting. All here you can write there, right? All this value you can set up. Detail you can read all this, right? So configure this built-in solution, right? Okay, and then enable whether you want to enable internal signal or not, right? So you must enable at least you see if let's say you want to do the measurement about the position, you need to do the homing. When the reference signal appears, then he will trigger internal signal, right? To you, etc. Right? At least you need to know this signal, right? So, and okay, what else? The rest should be output is quite straightforward, right? So this is for you to set because when you do the integration of a position, sometimes you may overflow. You may go to a very big number, otherwise overflow. So you must always set the maximum value for position. Go beyond that, don't increment, don't do the integration, right? Just cut off, right? Okay, so it's a threshold of the maximum value of the position, right? So you can set it. Then run, okay? So then basically you can get all these values, right? From a position, okay? Position register. Actually, you get this value of C minus CR. Just as I mentioned, because microcontroller do not know what is theta P from pitch angle of your encoder. So when you read the position, actually it's a C minus CR. The actual position must be C minus CR times the pitch angle. That is the actual rotating angle, right? Clear? So you must pay attention here. You can also read the velocity. Just as I mentioned, manufacturer of a microcontroller may not know what is the pitch angle theta P. So if you output C divided by theta T, the actual average velocity should be this number read from this register times pitch angle theta P, right? That is the actual angular velocity. Okay, so it's quite straightforward for you to know, right? Okay, and if let's say you want to know what is or you anticipate the reading, because if let's say you said I want to get to know the median of the velocity every 10 milliseconds. Sometimes you cannot wait. I want to, let's say I only have a 0.5 millisecond. I want to verify what is the velocity within 0.5 millisecond. You can read this theta T, which is not equal to, have not yet reached 1 millisecond. So you get from this register, that is the actual accumulated time, okay, which is not the total time window for you to do the measurement or partially observe the time to do the measurement, right? So you can anticipate the reading. Don't wait for the entire duration of the measurement time window to elapse, right? Okay, so this is just for you to know. You can also at any point in time to know what is the value of the C. No need to wait for the measurement time window to elapse, right? So in between, you can constantly monitor what is the actual value of the C. Okay, then you can do some prediction about the angular velocity. So this is good for you to anticipate the control because you want to do advanced control. Also, you set the cycle by cycle time is 1 millisecond, but without waiting for 1 millisecond to run out, right? So in between, you can still anticipate some action. Then you read this number and make a decision of what to do, right? Clear? Okay, it's just for you to know this, okay? And then you can check whether there's an internal signal produced at the hardware or not. Okay, so you go to this register to see whether internal signal appear, etc. Right? In particular, to see whether this reference position signal appear or not. Right? Okay, so this just for you to know. And then this is to clear for this interrupt. I always remember that if you decide to take action according to any one of these interrupt signal, after the action, always remember to clear. Otherwise, you will repeat doing the same action, right? Okay, so this is something you need to know. Otherwise, nothing special. This is for you to know the direction of the motion. This is interesting. Whether it's clockwise, counterclockwise, whether it's forward motion, backward motion, right? Or whether your hardware has error or not. So you verify the feed, etc. Okay, I guess this should be good enough already. Then these are the small exercises for you to go through. Then you know a little bit of familiarize with okay, little bit of knowledge of the interface between IoT and digital sensor, right? Okay, so then we still have maybe 10 minutes left for Q&A. Okay, so by now I believe more or less you know how to implement or choose your project, right? So from today's study, at least you know this I monitor or I build up a system to gain awareness about the area. Yes or no? This I gain awareness about the temperature in this building. How to do it? Based on today's study, you should be able to do it, right? This is gain awareness about the temperature, humidity inside this building, right? But today we do not have such information, right? Okay. Or eventually you may say in the village, right? Or in a big city, you want to constantly know what is the temperature distribution, or every hour or every half hour, you want to know humidity distribution. That should be good enough, right? Every half hour, it's not enough, humidity sensor to capture data, right? So based on today's study, you should be able to have some idea about the group project, right? Okay. Or in the production line, you want to monitor distribution of temperature, humidity, or in the farm, right? Or in agriculture, how to monitor. Okay. Some critical parameter, right?